So today I'm happy to present this work. And this is a joint work from Central South University, Xi'an Jiaotong University, and Tsinghua University. And as introduced by the session chair, I'm not the author from this paper. So because I cannot got a US visa. So today you get me instead. So I will do my best to present their excellent work, but all the credits goes to the authors, but all complaints, however, come to me. So actually why I choose to present on behalf of them is that when I was doing my PhD, congestion control was my first topic when I was trying to do. So this just reflects my memories during my PhD years. So in general, for congestion control, it needs to solve the complex traffic patterns inside the data center to help manage the traffic. So for traditional DCN workload, which focuses on providing good performance for short flows, they need to provide to maintain the queue length very small to guarantee ultra low latency. But recently, for the AI workload triggered by LLM traffics, it desires very high throughput. So the goal of the congestion control is to guarantee both ultra low latency for short flows and provide high throughput for long flows. So the key of it is to maintain the buffer or the queue length at a very steady point, which is small. So for lossless, it's need to minimize the trigger of PFC signals, which will cause head-on line blocking. And for lossy network, it need to minimize the packet losses so that it can minimize the impact of buffer overflow. So there are mainly two types of congestion controls inside data center. The one is to use a switch help to mark the queue length, like using ECN signals or INT signals. And the other type is, which this paper studies, is delay-based congestion control in data center. So for this type, it does not rely on any measurement from the switch, but it can directly use the delay signal measured on the endpoint to calculate the desired rate. So these delay-based approaches are easier to be implemented because it does not need any switch assistance. So for this type, existing work mainly focus on two things. The one is to how to get this accurate delay measured, and they have solved it perfectly. And the other thing is they need to use this delay to calculate the rate. And that's where we found existing work have issues. So the basic architecture of this delay-based approaches is that they first measure those delay signals, and they use a stage called congestion information deduction, or CiD. In short, it used this to compute the delay and the delay gradient to reflect the congestion conditions in the network. And then they calculate the rate according to the CiD signals they got, and finally adjust the sending rate of this endpoint. And however, we do experiment to study it. Previous work have shown that these delay signals may be inaccurate, but we have done a comprehensive study to show three conditions that may lead to the delay signal where cannot reflect the real congestion in the network. So This is a first condition. And the left figure is the delay signal, and the right figure is the gradient of delay signal. So for the first case is that when the descending rate of the flow is smaller than the bottleneck capacity. In this case, the delay signal cannot reflect the congestion condition, especially this underutilized condition, because if the queue is empty, then the delay signal is unable to detect whether the injection rate is lower than the bottleneck capacity. So for this case, both the delay signal itself and the gradient is far from the actual congestion status. And the second case is when there are many concurrent long flows inject into this network, and the delay signal will react slower than the real case because it needs to measure the status on the endpoint. So as you can see from this figure, so from the left figure, which reflects the delay signal itself, you can see compare with those switch-assisted solutions. The signal has the curve, which ascending curve, but actually when the endpoint gets the highest signal, the congestion actually already being solved. So this makes the delay signal less effective than those switch-assisted ones. So for this case, the endpoint is hard to adjust rate purely based on this inefficient signal. So the third case is when there are many short bursty flows inject into the bottleneck link. And as you can see, the delay itself is steady, but the gradient of delay actually has a very high variance, as you can see from the right figure. So for this case, the signal, the endpoint cannot use the signal to directly to get a steady state of the congestion status. So it's hard for those approaches to adjust their ascending rate. And we have an analysis of the existing solutions, and we find that for timely and swift, they ignore some of the rich information carried in this delay signal, but it chooses to just use this signal to get them to do a search in the available bandwidth and to then check the effect, so which leads to a slow convergence. Another one is theta PowerTCP, which try to use all this rich information in the delay signal, but due to the seed inaccuracy when what I have talked before, they may react wrongly to the congestion. So this leads to the motivation of this paper. So instead of directly use the seed measured to adjust sending rate, we add another layer which to justify whether the seed signal is trustworthy. So for trustworthy cases, we can use an equation to directly compute the rate. But for the untrustworthy scenarios, we can only do the rough direction to search for the sending rate, which is like the timely and the swift. So there are two challenges of achieving this. So the first one is how to know the CiD trustworthiness. Our intention is to divide the system into two regions based on whether the system can tolerate the effect of the inaccurate delay signal. And so we have a deeper analysis on how the congestion control need to react to different congestion states, and we divided it into three areas. So this red marked areas is where the system can tolerate any inaccuracy of the signal. So for this case, the congestion control can directly calculate the rate, but for others, they need to probe for the rate. So for the details of how to divide these regions, please refer to the paper. And the second challenge is how to adjust the rate. Even if we have divided regions, but how to react to the congestion states to avoid any side effect if the signal is inaccurate. And also we need to use these states to further enhance how we evaluate the CiD trustworthiness. So our intention to do this is that we adopt different rate adjustment rules in different regions. And for the CiD trustworthy regions, we use an analytical rate adjustment way to directly compute the right sending rate. So by using this, the convergence of our approach can be very fast. And for other regions, we actually use a probing method to search for the right sending rate inside the searching space. So I will skip all the details of how we get these detailed equations, because they are so mathematical, which as a non-author, I'm not very familiar with. So we have implemented this using a DPDK. So we found that we implemented a very lightweight way to calculate those equations, so that we believe even this can be easy to implement in the real hardware. And we also make the per connection states minimized so that it does not include a high overhead. So then it comes to the evaluation. So we first do an experiment on the real testbed. We compare with DCQC, which is not a delay-based one, because none of the delay-based one has been supported by the real hardware. So as you can see from the figure, CCC react very fast to the congestion, and that directly let the sending rate of the two flows come to the fairness point. But for DCQC, it takes a very long time to react to the congestion and searching for the right sending rate. And we also compare with other congestion controls using simulation. And we can see they are doing better than DCQC, but it's still due to the special conditions which I talked at the beginning of my talk, they cannot converge very fast to the congestion as Swift cannot use the equation, analytical equation model like us, and for HPCC it also cannot have this fast convergence. So we also measure those details of why this our CCC approach can have better condition, but better performance. But I will skip this, and also we have used very comprehensive evaluations on multiple scenarios, and we show that CCC can have the best average link utilization, smallest tail latency, and other metrics. And we also evaluate on the real workloads. So for a traditional data center workload, we provide a lower tail latency and the average latency compared with all other congestion control methods. And we also evaluate using the AI model training workload, and we found that CCC can provide the lowest completion time for the model training, which prove that the CCC can adapt the congestion among the best of these approaches. So in conclusion, we have three things. We provide three things. The first one is that we prove that the CID signal can be untrustworthy even with precise delay measurements. And the second one is that we provide this CiD-sensitive architecture for delay-based congestion control. And the third is that we evaluate our approach CCC and compare with other congestion control algorithms, and we found the CCC can provide best performance among them. Yeah. Thank you. I'm happy to take any questions.